I can see Andre. Is the screen sharing working?
I hope so. Let's try. I'm embarrassed to say that I barely use Zoom. I know this is shocking.
Yes.
Let's see.
Okay. Yeah. Seems still to work, even with limited experience. Okay, so it's a pleasure to introduce Andre. I have to say, I think he doesn't really need a lot of introduction. But yeah, he is the senior director of AI at Tesla, and he basically supervises and leads the team responsible for all the neural networks in the autopilot. With this, it's a pleasure to have you here, and I'm really looking forward to your talk.
Yeah, great. Thank you for the introduction. And I'm very happy that I was able to display some impressive zero-shot learning on Zoom. Okay. Yeah, so I'm very excited to be here. Thank you for the introduction. I would like to talk a bit more about what Tesla has been up to over the last few months. So first to start, I guess we are here at the CVPR workshop on autonomous driving. So I think I'm preaching to the choir a little bit, but I'd like to start with some slides on like why we're doing all of this. And I think, unfortunately, we're kind of like in a bad shape when it comes to transportation in society. And basically the issue is that we have these metallic objects traveling incredibly quickly and with very high kinetic energy. And we are putting meat in the control loop into the system. And so this is quite undesirable. And really fundamentally what it comes down to is people are not very good at driving. They get into a lot of trouble and accidents. They don't want to drive. And also, in terms of economics, we are involving people in transportation. And of course, we'd like to automate transportation and really reap the benefits of that automation in society. So we all, I think, are on the same page that it should be possible to replace the meat computer with a silicon computer and get a lot of benefits out of it in terms of safety and convenience and economics. So in particular, silicon computers have significantly lower latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram, and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a feature. This is a frame from iRobot, a really good movie if you haven't seen it. And here, Will Smith is about to drive a car manually. And this other person here is shocked that this is going to happen. This is ridiculous. Like, why would you actually have a human driving cars? And so I think this is not very far from truth. And this movie is taking place in 2035. So I think by then, I actually think this is a pretty prescient prediction. So what I think is kind of unique about Tesla and in our approach to autonomy is that we take a very incremental approach towards this problem. So in particular, we already have customers with the Autopilot package, and we have millions of cars, and the Autopilot software is always running and providing active safety features, and of course, the Autopilot functionality. So we provide additional safety and convenience to our customers today, and also the team is working on full self-driving ability. So I would briefly like to very quickly speak to the value today that we provide, just to give you some examples of what the team is up to and what we're sort of doing today. So here's an automatic emergency braking scenario. So the driver here is proceeding through an intersection, and you can see trouble coming here. So the person kind of crept up from here, and the car sees the pedestrian, object detection kicks in, and we slam on the brakes, and we avert a collision. Here's an example of a traffic control warning. So this person is probably not paying attention, potentially on the phone, is not braking for the traffic lights ahead, but we see that these are relevant traffic lights. They are red, and we beep, and the person immediately starts slowing and probably does not actually enter the intersection. These are examples from pedal misapplication mitigation, PMM. Here, a person is unparking from their driving spot, and they are trying to turn, and then they mess up, and they accidentally floor it. So they floor it right there, and the system kicks in. It sees pedestrians ahead of us, and it slams on the brakes and averts what would be a very gnarly situation in this case. Here's another last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system, again, sees that there's no driving path forward and actually slams on the brakes and averts. In this case, this person is not going to be swimming in this river imminently. So these are some examples of the value that we are providing today in this incremental autonomy fashion. But of course, the team is actually... Sorry about that. The team is working primarily on the FSD functionality, which is our full self-driving suite. So here we have the FSD beta product, and it's in the hands of about 2,000 customers. And this is an example from one of the customers driving around San Francisco. And these people are posting videos on YouTube, so you can check out a lot of videos. But what we're showing here on the instrument cluster is we're showing all of our predictions. So you're seeing some road edges, some lines, some objects, and the car, of course, is navigating around autonomously here in San Francisco environment. Now, we, of course, drive this extensively as engineers. So it's actually fairly routine for us to have zero intervention drives, I would say, in like sparsely populated areas like Palo Alto and so on. I would say we definitely struggle a lot more in very adversarial environments like San Francisco. A lot of people working in autonomy, of course, know all about that as well. So this drive ends up being a fairly long drive, and it's zero interventions in this case. Now, one thing I like to point out always whenever I show the video of Tesla driving around autonomously in these city environments is you've seen this before, and you've seen it for a decade or more. So here's a Waymo taking a left at an intersection. And this is actually a pretty old video, I believe. And so you've been seeing stuff like this for a very long time. So what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment with the LiDAR sensor, and you have to create a high definition map. And then you have to insert all of the lanes and how they connect and all the traffic lights and where they are. And you basically have to create a high definition map. And then at test time, you are simply localizing to that map to drive around. And so the approach we take is vision-based primarily. So everything that happens for the first time there in the car based on the videos from the 8 cameras that surround the car. And so we come to an intersection for the very first time, and we have to figure out where are the lanes, how do they connect, where are the traffic lights, which ones are relevant, what traffic lights control what lanes. Everything is happening at that time on that car, and we don't have too much high definition sort of information at all. And this is actually a significantly more scalable approach, because if our product is on a scale of millions of customers on Earth, and so it's actually quite unscalable to actually collect, build, and maintain these high definition LiDAR maps. It would be incredibly expensive to keep this infrastructure up to date. And so we take the vision-based approach, which of course is much more difficult because you actually have to get neural networks that function incredibly well based on the videos. But once you actually get that to work, it's a general vision system and can in principle be deployed anywhere on Earth. So that's really the problem that we are solving. Now, in terms of the cartoon diagram of a typical sensing suite of an autonomous vehicle, these are kind of like the typical sensors you would see. And as I mentioned, we do not use high definition maps and we do not use LiDAR. We only use video cameras. And in fact, the vision system that we have been building over the last few years has been getting so incredibly good that it's kind of leaving a lot of the other sensors in the dust. And so actually, the cameras are doing most of the heavy lifting in terms of the perception that you've seen in the car. And actually, it's gotten to the point that we are able to start removing some of the other sensors because they are just becoming these crutches that you start to not really need at all. So actually 3 weeks ago, we started to ship cars that have no radar at all. So we deleted the radar, and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in his tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically, like, vision is getting to the point where the sensor is like 100x better than, say, radar. Then if you have a sensor that is dominating the other sensor and so much better, then the other sensor is actually starting to like really contribute, it's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision-only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision-only control without radar, and how we have released this quite successfully so far to the fleet, and what it has sort of taken for us to do that. So here I wanted to show a video, basically showing what the input of the system is. So we have 8 cameras surround, and these are fairly high definition cameras, and we have 36 frames a second. And you can see that basically you can actually understand a lot about this environment from this input. It's extremely information rich. You're getting a huge amount of constraints, 8 million bits roughly of constraints, per second on the state of the surroundings. And so it's incredibly information rich compared to any other sensor you may want to have in a car. And so this is the one that we're doubling down on, because this is ultimately where all the difficult sort of scene interpretation challenges lie. So we prefer to just focus all of our infrastructure and development on this. And we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team. Now, typically when we talk about vision, the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is it gives you a quite accurate depth and velocity measurement. It's a pretty direct measurement of the car ahead of you in very nominal situations. So here I'm showing a random image on the left, and you are seeing the depth, velocity, and acceleration reported by the radar stack for this car. And you can see that it's a bit wiggly on the velocity, so this is some kind of a stop and go scenario. Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is, like, once in a while, at random, it will give you a dumb measurement, and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem, and we need a massive data set of depth, velocity, acceleration on a lot of cars, and we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach, and that actually works really well if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have three properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples of that. So first of all, how are we going to achieve this data set? So of course, we need to collect training data. The typical approach might be to use humans to annotate cars around us in 3 dimensions. What we found actually works really well is an auto-labeling approach. So it's not pure humans, just like annotating cars. It's an offline tracker, as we call it. And it's an auto-labeling process for collecting data at the scale that is necessary. So we need, again, millions of hard examples. So this is where the scale comes from, is that it's not labeled purely by humans, although humans are involved. It's labeled automatically. So here's an example of some automatic labels we were able to derive for cars on the highway. And the way you do this is, because you are offline and you are trying to just annotate a clip, you have a large number of benefits that you don't typically have if you're at test time under strict latency requirements in the car. So you can take your time to fully figure out exactly all the objects and where they are. You can use neural networks that are extremely heavy, that are not deployable for various reasons. You can use benefit of hindsight because you know the future, not just the past. You can use all kinds of expensive offline optimization and tracking techniques. You can use extra sensors. In this case, for example, actually radar was one of the sensors that we used for the auto labeling. But there's actually a massive difference between using radar at test time and using it in the offline tracker. And that is that at test time, a radar can just report a stationary track immediately in front of you, and you have 20 milliseconds to decide if you're going to brake or not. If you're offline, you have the benefit of hindsight. And so you can do a much better job of calmly fusing if you really want to. And so there is a massive difference there. And in addition, you can, of course, involve humans, and they can do cleaning, verification, editing, and so on. And so we basically found that this was a massive lever to allow us to reach the scale and the labeling quality. And then to get the diversity, that was also a massive fight. So here's some examples of really tricky scenarios. So here, there's some, I don't actually know exactly what this is, but basically this car drops a bunch of debris on us, and we maintain a consistent track for the label. And of course, if you have millions of labels like this, the neural net, if it's a powerful enough neural net, will actually end up learning to persist these tracks in these kinds of scenarios. Here's another example. There's a car in front of us, and I actually am not 100% sure what happens in this case, but as you'll see, there's some kind of a dust cloud that develops here and briefly occludes the car. But in the auto-labeling tool, we are able to persist this track because we saw it before and we saw it after, so we can actually stitch it up and use it as a training set for the neural net. Here's one more example of an adversarial scenario from heavy snow. Again, we can auto-label this fine and create a large collection of examples. Now, as we were working on this over a duration of, I want to say, of roughly 4 months of really just focusing a lot of the team on this problem of achieving really good depth, velocity, and acceleration, we've ended up developing 221 triggers manually that we were using to source data from our customer fleet. And this is just an example, some examples of the 221 triggers that were used to collect all of these diverse scenarios. So for example, we have shadow mode, where we deploy a neural network that is pretty good at predicting depth and velocity. And what we do is we run it silently in the cars of our customers, but it's not actually connected to control. What's driving is the legacy stack. But we're basically running the new measurements of depth and velocity, and we're, for example, looking at whether or not they agree or disagree with the legacy stack or with the radar. We're looking for other sources of jank, like, for example, if there's bounding box jitter, detection jitter, the main and the narrow camera disagree. We predict that there's a harshly decelerating object, but the person seems to not mind. All kinds of disagreements between different neural network signals. And there's a long list here. It took us a while to actually perfect these triggers, and all of them are iteration, and you're looking at what's coming back, you're tuning your trigger, and you're sourcing data from all these scenarios. So basically, over the last 4 months, we've done quite extensive data engine, and we've ended up doing 7 shadow modes and 7 loops around this data engine here, where on the top right is where you begin. You have some seed data set. You train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described. You're getting these scenarios where the network is probably misbehaving. Some of those clips end up going to unit tests to make sure that we, even if we're failing right now, we make sure we pass later. And in addition, those examples are being auto-labeled and incorporated into a training set. And then as a asynchronous process, we're also always data cleaning the current training set. And so we spin this loop over and over again until the network basically becomes incredibly good. So in total, we've done 7 rounds of shadow mode for this release. We've accumulated 1 million extremely hard, diverse clips. And these are videos. So these are, you should roughly think about, say, 10-second clips, 36 FPS, something like that. In total, we have about 6 billion objects labeled cleanly for depth and velocity. And this takes up roughly 1.5 petabytes of storage. So that gives us a really good data set. Of course, that by itself does not suffice. So we have an incredibly good AI team that is designing the neural network architecture. There's basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by a transformer, by a recurrent neural network, or just by 3-dimensional convolutions. We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at that time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I'm someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals. And so I can work in isolation to some extent and actually get something to work pretty well. And then once in a while, so basically the iteration scheme is that a lot of people are fine tuning, and once in a while we do an uprev of all of the backbone end to end. And so it's a very interesting sort of mechanism, because we have a team of roughly 20 people who are, I would say, training neural networks full time, and they're all cooperating on the single neural net. And so what is the workflow by which you do that is pretty fascinating, and continues to be a challenge to actually design efficiently. So we have a neural network architecture, we have a data set. Now, training these neural networks, like I mentioned, this is a 1.5 petabyte data set, requires a huge amount of compute. So I wanted to briefly give a plug to this insane supercomputer that we are building and using now. For us, computer vision is the bread and butter of what we do and what enables the autopilot. And for that to work really well, you need a massive data set. We get that from the fleet, but you also need to train massive neural nets and experiment a lot. So we've invested a lot into the compute. In this case, we have here a data set. We have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. And we have also a very efficient fabric that connects all of this. Because of course, if you're doing distributed training across your nodes, you need your gradients to be synchronized very efficiently. And of course, we are reading all of these videos from the file system, and that requires a really fat pipe as well. So this is a pretty incredible supercomputer. So this is a GPU cluster. Next up, we're really hoping that we're currently working on Project Dojo, which will take this to next level. But I'm not ready to sort of reveal any more details about that at this point. What I would like to do is I would like to just briefly plug the supercomputing team. They've been growing a lot. And so if high performance computing for this application and for training these crazy neural networks excites you, then we would definitely appreciate more help. So please contact the supercomputing team at supercomputing at Tesla to help us build these clusters. On the left here, we have the compute nodes, and on the right, this is a network switch, actually. So the wires here is kind of like the white matter of this synthetic cortex, I guess. The other thing I wanted to briefly talk about is I wanted to also mention briefly that this effort basically is incredibly vertically integrated in the AI team. So as I showed you, we own the vehicle and the sensing, and we source our own data, and we annotate our own data, and we train in our on-prem cluster, and then we deploy all of the neural networks that we train on our in-house developed chip. So we have the FSD computer here that has 2 SoCs, FSD chips here, and they have our own custom NPU neural processing unit here at roughly 36 TOPS each. And so these chips are specifically designed for the neural networks that we want to run for FSD applications. And so everything is very vertically integrated in the team. And I think that's pretty incredible because you get to really co-design and engineer at all the layers of that stack. And there's no third party that is holding you back. You're fully in charge of your own destiny, which I think is incredibly unique and very exciting. And then we have a deployment pipeline here where we take these neural networks and we do a lot of typical graph optimization, fusion, quantization, threshold calibration, and so on, and deploy it on our chip. And and this is in the customer's cars, and these neural networks run there. So now what I'd like to show is, I first would like to show some qualitative examples of some of our results in terms of the depth and velocity predictions that we were able to achieve by putting all of these pieces together and training these networks at scale. So the first example here, I have a video where this is on track testing. So this is an engineering car, and we asked it to slam on the brakes as hard as it possibly can. So this is a very harsh braking here in front of us. Even though it doesn't look like that in the video, this is very harsh braking. So what you can see on the right here is you can see the outputs from the legacy stack, which had radar vision fusion, and from the new stack, which is vision alone in blue. So in the orange legacy stack, you can actually see these track drops here when the car was braking really harshly. And basically the issue is that the braking was so harsh that the radar stack that we have actually ended up not associating the car and dropping the track and then reinitializing it all the time. And so it's as if the vehicle disappeared and reappeared like 6 times during the period of this braking. And so this created a bunch of artifacts here, but we see that the new stack in blue is actually not subject to this behavior at all. It just gives a clean signal. In fact, here, there's no smoothing, I believe, on the blue signal here. This is the raw depth and velocity that comes out from the neural net, the final neural net that we released with about 3 weeks ago. And you can see that it's fairly smooth here. And of course, you could go into the radar stack and you could adjust the hyperparameters of the tracker, like why is it dropping tracks and so on. But then you are spending engineering efforts and focus on a stack that is like not really barking up the right tree. And so it's better to, again, just focus on the vision and make it work really well. And we see that it is much more robust when you train it at scale than something like this. Here's another example, fairly infamous example of slowdowns when there are cars going below a bridge. The issue here, again, is that the radar does not have too much vertical resolution. So radar reports a stationary object in front of you. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two. So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct. And then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then you brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case. Because we just get the correct depth and velocity, and vision obviously has the vertical resolution to differentiate a bridge from a car and whether or not the car is slowing or not. So again, you could go into the radar stack or the sensor fusion stack, and if you have an improved depth and velocity, you could change the fusion strategy. But again, you're just kind of like doing dead work. Like this signal is so good by itself. Why would you do that? So in this setting now, we've improved the situation quite a lot. Here's another last example. We have a stationary approach. Again, this is in track testing environment. This is an example of a test that we would run. And we are just approaching this vehicle and hoping to stop. What you see in orange in the legacy stack is that it actually takes us quite a bit of time for us to start slowing. And basically what's happening here is that the radar is very trigger happy and it sees all these false stationary objects everywhere. Like everything that like sticks out is a stationary target. And radar by itself doesn't know what actually is a stationary car and what isn't. So it's waiting for vision to associate with it. And vision, if it's not held up to a high enough bar, is noisy and contributes sort of error. And the sensor fusion stack just kind of like picks it up too late. And so again, you could fix all that, even though it's a very gross system with a lot of if statements and so on, because the sensor fusion is complicated because the error modes for vision and radar are quite different. But here, when we just work with vision alone and we take out the radar, vision recognizes this object very early, gives the correct depth and velocity, and there's no issues. So we actually get an initial slowdown much earlier. And we've really like simplified the stack a lot and as well. So just speaking very briefly to the release and validation, we've extensively validated this before we, of course, ship this to customers. Just some example numbers for the validation itself. We've handpicked about 6,000 clips in about 70 categories of scenarios, like harsh braking, crossing vehicles, different vehicle types, environments, and so on. And we run these tests on all the commits of the build, and we run them also every day periodically as we were trying to drive up the performance on these clips. We also use simulation extensively for validation. We've also used simulation for training, although I haven't gone into that, but we've had some successes there. But we use it primarily for validation at this stage. And that's, again, like diversity of scenarios, trying to make sure that the stack is performing correctly. We've done a lot of track testing, and I've shown you some examples of that. We've driven this extensively in the QA fleet, and we've also deployed this in shadow modes and seen that this stack performs fairly well. So in particular, for example, for the automatic emergency braking, we actually see a higher precision and recall compared to the legacy stack that is a fusion stack. And so having seen all this, we've actually released this. We've accumulated about 15 million miles so far. And 1.7 million of those have been on autopilot. And so far, there have been no crashes. Now, of course, we're running at massive scale here. And so we do expect some crashes at some point. The legacy stack has a crash roughly every 5 million miles or so, I believe. And so we do expect some incidents at some point. But the improvements for the vision stack are not sort of stopping. So I think we're very confident that we're barking up the right tree here and that we can actually get this to work really incredibly well. I also wanted to briefly give a shout out to auto labeling as an incredibly powerful method for sourcing training data. So we're applying auto labeling to all of the FSD tasks, not just to depth and velocity of the car in front of us. Here's an auto labeler for pedestrians. And you can see that the tracks are very smooth. And this is, again, a completely offline process that we are applying not just to objects, but also to a lot of static environments. So this is some example of a 3D reconstruction. So here we see a clip, and this is a vision-only estimate of the depths of all the points. And of course, you don't actually want to really deploy these measurements directly into a car because they are too raw. So what you actually want to do is you want to, again, auto-label. And you want to really think about what is the information I really need at test time in the car? And what is like as close as possible to action, right? So you want to do all this work at training time, figure out exactly what happened in the clip, reconstruct the entire environment, and then you want to actually like post-process the curb at training time. So you want to do as much at training time and labeling time as possible. And then you want to figure out what are the tasks I really need at test time. And that's the thing that happens in the car, subject to very strict latency requirements. You want to do as little post-processing there as possible. So we see that this is a very powerful lever on creating data sets. So in summary, what I try to argue and give you a sense of is vision alone is actually, is our finding that this is perfectly capable of depth sensing. It is an incredibly rich sensor in terms of bandwidth of information. And doing this and matching radar performance and depth and velocity is incredibly hard. I believe it requires the fleet because the data set that we were able to achieve was critical in all these performance improvements. And if you do not have the fleet, I'm not 100% sure how you can source all the difficult and diverse scenarios that we did source, because I believe that was critical to getting this to work. So it's hard, it requires massive networks, a supercomputer, and a data engine, and the fleet. But all of these components are coming together in a vertically integrated fashion at Tesla AI. And I believe that this makes us sort of uniquely positioned in the industry where we are barking up the right tree, and we have all the puzzle pieces to make this work. And so if you are excited about this approach that we're taking and the networks and the work that we're doing, then I would encourage you to please apply and join the team and help us make this a reality. So you can go to tesla.com/autopilotai. It's a very simple process. You upload a resume and you have a blurb about some of the things that you've done that are impressive. And then that comes directly to us. And we'd love to work with you to make this a reality. Thank you.
Thanks for this very, very interesting talk. We actually got quite some questions. Since we are already over time, I will limit it to a few. We are at the kind of nice point at the end of the workshop, so you are a bit of a rough spot that you have to answer more questions than maybe other speakers. And kind of, I would like to go as the first one into the, kind of the maybe a bit the auto labeling, but actually the thing which really is necessary for the auto labeling, and this is these, this definition of these triggers.
Yep.
Did you ever try to investigate if you can automatically generate those triggers?
That's an interesting question. So the triggers are kind of like, they're designed based on what we're seeing and what's coming back in the telemetry from the cars. So we are seeing clips where maybe we didn't brake, but the person did, or vice versa. There's all kinds of disagreements with like human driving and the legacy stack. And we're looking at this, and typically we try to have signals of various generality. So for example, like a vision radar disagreement is a very general trigger. It can source all the disagreements. And then there are very specific ones, like maybe we struggled actually for a while when we were entering tunnels and exiting tunnels because there was a lot of brightness variation. So we struggled a lot there as an example. And we had to specifically design some triggers for that because we were not catching it with a high enough frequency. Because for any of these situations, you actually need to make sure they're represented well in the training set. So for us, this was a fairly manual process, but we do have a team basically dedicated to doing this full time, and they did this for 4 months. So I don't, how do you automate this? I think is a very tricky scenario because, again, you can have these general triggers, but I think they will not correctly represent the error modes. And I think it would be really hard to, for example, automatically somehow have a trigger that triggers for entering and exiting tunnels. That's something semantic that you as a person have to like intuit that this is a challenge for whatever reason and actually go after it specifically. So yeah, it's not clear how that would work, but I think it's a really interesting idea.
Yeah. So, I thought it sounded very interesting. The question sounded very interesting and not easy to answer.
Yeah.
Maybe another one, which actually in somehow, let's say, 2 version showed up a bit, was kind of in your vision only approach. Kind of, could there be other sensor, like, for example, thermal image, kind of thermal cameras, which could help you in low light situation, or actually even the radar, which could kind of give you some very specific information. I think there was an example of radar signals bouncing through basically the car before you, and then you still get somehow a signal of the car, one ahead, things like that. Do you think really vision is enough, or kind of, maybe some special sensors which could give you a certain edge?
Yeah, I think it's an interesting idea. I would say, like, clearly people use vision and the visual spectrum, and they make it work. And so there's an infinity sensors of varying economic costs. Actually, vision and in the visible light spectrum is incredibly cheap sensor, right? So the economics of this are very appealing, and you can actually manufacture and include this at scale. So it's a very cheap and nice sensor. And I would say that basically we have proof from humans that it is sufficient. And I would say also that vision has all of the information for driving. So I would say that basically vision is necessary and sufficient in my mind. And so we're primarily focusing on that. And you could go crazy with a lot of sensors, but I think we're definitely currently just like doubling down on that alone.
Yeah, thanks a lot. I think we are now already more than 5 minutes overtime. So I let you go and don't ask other evil LiDAR versus camera questions. With this, I would actually like to give some kind of concluding remarks on the workshop, or better, move over to the last part. So before, I would really like to thank the whole team. Without them, this would have never been possible.
So I'm very excited to be here to tell you a bit more about how we're scaling machine learning models, data algorithms, and infrastructure at Tesla and what that looks like. So the rough outline of my talk is here. I'd like to first tell you a little bit about Tesla Autopilot, what the feature set is, really what the problem statement is, what we're trying to address here. Then I'll tell you a bit about neural networks and what it takes to actually deploy them into production at scale and what that looks like for the team. And then I'll tell you a little bit more about some of the more recent neural networks that we have developed for the purposes of full self-driving. So I'll go into that at the end. So first, a little bit about Tesla and Tesla Autopilot. So as you may know, Tesla manufactures and sells electric vehicles. We have a whole array of electric vehicles. Some of them are in the hands of customers or imminently to be in the hands of customers, and some of them have only been announced. So for example, we have the Model S, the Model 3, X and Y, and then we've also announced the Cybertruck, the ATV, somewhat jokingly, the Roadster, and the Semi. And we have quite a few of these. So globally, we now have roughly 1 million cars. And for the purposes of the team, these are not just cars, these are computers. They're internet accessible, and we can both deploy over-the-air updates to them and get a lot of data from them that helps us develop the autopilot. And they're also robots, so they have sensing, they have actuation, and we're developing the brains of that computer. Now, the most basic kind of autopilot functionality is that when you turn it on in your car, the car will keep its lane and it will keep distance away from the vehicle ahead of you. We've now sort of accumulated almost 3 billion miles on the autopilot, which sounds like a lot. We then have more advanced features, like such as, for example, Navigate in Autopilot. This allows you to set a pin somewhere in the world as a destination. And then as long as you stick to the highway system, the car will automatically reach that destination on the highway system. It will do all the correct lane changes. It will take all the right forks at interchanges, and it will overtake slow vehicles ahead of you. And it's kind of like, we think of it as roughly autonomy on the highway. And the car now has to monitor its blind spot. It has to have intelligence around where it is on the highway. It has to localize the correct lane and so on. We've also late last year released a smart summon. This allows you to, with your phone on the mobile app, summon the car to you from a parking spot. So if your car is parked somewhere, you just summon it to you, and the car comes out of its parking spot with no one inside and wind its way through the parking lot to come find you. It's quite magical when it works. Also under the hood, we have a lot of active safety features that are always running and available, even when autopilot is not turned on. And we have a lot of statistics available to us because we have 1 million cars on the road, and we know how people get into trouble. And then we try to implement features that help alert or avert an accident. So for example, automatic emergency braking, front collision warning, side collision warning, blind spot monitoring, lane departure avoidance, emergency lane departure avoidance, and so on. These active safety features help keep customers safe in our cars. In particular, on active safety, we're doing extremely well. Euro NCAP awarded us with a 5-star rating. In particular, I believe we had the top scores in safety assist. We also did extremely well on AEB, automatic emergency braking for pedestrians and cyclists. Now, you're seeing here, for example, AEB pedestrian is 5.6 out of 6 points. I think these numbers are kind of like slightly abstract. So let me actually put that in context. Like, really, what are we talking about here? Pedestrian AEB is the following. Here's one example. The car just, someone just emerges from in between parked cars, and this car may not have even been on the autopilot, but we continuously monitor the environment around us. We saw that there was a person in front, and we slam on the brakes automatically. Here's another example. Looks like a pretty benign scene. This person is probably not paying attention. The pedestrian is not paying attention. We slam on the brakes and prevent a collision. Here's one more example. You can see the trouble coming from the right. It's really hard to tell because everything is occluded, and then suddenly there's a pedestrian. We slam on the brakes and avert a collision again. So 5.6 out of 6 is kind of abstract, but we see a lot of these. We see tens to hundreds of these per day where we actually are averting a collision. And not all of them are true positives, but a good fraction are. And this is where you actually make your object detector really count. You're really averting collisions. Now, the goal of the team, however, is to produce full self-driving functionality. So here we have a video from the Autonomy Day that we had somewhere earlier last year. Whoops. There we go. The ambition of the team is to produce full self-driving, meaning that you can just set a pin arbitrarily in the world, not even on the highway system, but everywhere else. Here you see the car just taking turns from the parking lot. It comes to an intersection. It waits for a green traffic light. It turns to the left, merges on the highway, and no need to touch the wheel. This is not available to the customers. We only have developer builds that do these turns through intersections and so on. But we're trying to get it to the point where we feel that the system is accurate enough to actually release in some form. So I'm going to cut this short, but this will actually get on the cloverleaf in a bit. It will take the cloverleaf, it will turn around and come back to our headquarters in Palo Alto, where a lot of the team is based. Now, I'm going to cut through this. You may be asking, you saw the car take a left through an intersection when the light was green. And you've actually seen a lot of these videos for like a decade. So, here's a Waymo. I just took a small clip. A Waymo comes to an intersection and takes a left through the intersection. You've seen this for a decade. So how is this special? Why are we so late? What's taking so long? And it looks the same. So I think the critical point to make is that it looks the same, but under the hood, it's completely different in terms of the approach that we take towards full self-driving. So in particular, we take a heavily vision-based approach. So everyone else has a LiDAR on the top of the car. The LiDAR shoots out lasers and creates a LiDAR kind of point cloud map. And then you pre-map the environment that you're going to drive. So you have a high-definition LiDAR map, and you localize to it to a centimeter-level accuracy. And then you know exactly the path you're going to take, so you can just steer to keep yourself perfectly localized in the correct region. So this is quite helpful, but this is not the approach that we take. We do not have LiDAR on our cars, so we don't shoot out lasers. It's all camera-based. And we do not build high-definition maps. So when we come to an intersection, we encounter it basically for the first time. We come to an intersection. How many lanes are there? Left, right, center? Which way should I turn? What are the traffic lights? Which lanes do they control? All of this is just done just from camera vision alone. And so this is a bit of a harder problem, but of course, once we actually get this to work, we can also deploy it to the millions of cars that we have globally. So let me now tell you a little bit about the neural networks that actually support all of the features that I've shown you that the autopilot is capable and what it takes to actually keep these neural networks in production at scale in the hands of customers. So here's a random scene where we have to potentially drive and wind our way through this scene. As a human, this is relatively effortless, but you're actually doing a lot under the hood, and the autopilot has to as well. So we have to understand a lot about what are the static objects, what are the dynamic objects, what is the road layout, what is all of the layer of semantics on top of the road, like lane line markings, road markings, traffic lights that tell you about how you can actually traverse that scene. So once you actually start writing down what's necessary to actually perform the driving policy, you end up with a long list of tasks, all of which we need to actually handle. And the detection of these tasks serves two purposes and two customers. Number one, we actually need it for driving policy. And number two, we actually want to show a lot of things on the instrument cluster for the human so that they gain sort of confidence in the system. Here we've produced a video that shows some of the under-the-hood predictions for the main camera that is facing forward on the car. And you see that we're detecting lanes, we're detecting stop sign over there, a stop line, road markings, we're putting cuboids around cars, traffic lights, road edges and curbs, even things like trash bins coming up over there, lines that make up the intersection. In a bit, there's lines that create parking spots. We have to have all these attributes for whether or not a line is for a parking spot or not, and things like that. So these predictions look pretty decent, but it's actually a huge amount of work to get them to actually work at scale and in the full long tail of what you can encounter on the roads. So even taking a very simple task, like for example, stop sign, you think that neural networks are capable of handling thousands of categories of ImageNet with all of their variations and so on. So how difficult is it to just detect a fixed pattern of like red on white stop? And it actually gets quite difficult when you get to the long tail of it, even to create a simple detector for a stop sign. So first of all, stop signs can, of course, be in lots of variant environmental conditions. Stop signs can not just be on poles, but kind of just like on walls. Stop signs can be temporary and just hang out in different configurations. Stop signs can have funny lights on them, which are supposed to make it easier to see the stop sign, but for our system it's the opposite. We have to actually explicitly worry about it. Stop signs can be held by a person. That stop sign can be in an inactive state or an active state. Stop signs can be on like these cones. Stop signs can be heavily occluded in lots of ways, by foliage, by signs. Stop signs can be occluded by cars. Stop signs can be part of cars, and they can be part of cars in an active or inactive state again. Stops can be sort of held by a person. Stops come with lots of exotic modifiers to them. So this stop only applies except right turn. This stop says take your turn through this place. This stop is right turn, keep moving. So do not stop if you're going right. So there's a variety of modifiers, all of them we have to care about because they actually have impact on how you should drive through this point of space. And as I mentioned, everything is AI vision based at the moment. We do have maps, of course, that we build, but they're not high definition maps. But stops can be attached to gates, but they only apply when the gate is closed. When it's open, they do not apply. Stops can be on arms. These arms can lift, and then the stop sign does not apply anymore. Stops can only apply when you're taking a left, so they're action conditional. And so basically there's a massive variety of, even just for a stop sign to get this to work. And what we do day to day in the team is we are going through the long tail, and we're building all this infrastructure for sourcing all these additional examples. And so I've shown in the Autonomy Day presentation earlier last year the data engine, the process by which we iteratively apply active learning to source examples in cases where the detector is misbehaving, and then we source examples in those, and we label them and incorporate them into part of a training set. So for stop sign detection, as an example, we have a approximate detector for stop signs based on an initial seed set of data, and we run that and deploy that to cars in shadow mode. And then you can detect some kind of a lack of health of that detector at test time. So for example, the stop sign detection is flickering. That could be a source of uncertainty. You can also detect that the neural network is uncertain in a certain Bayesian way, and there's a few ways to model that. You can find instances where you get surprised to see a stop sign, like why didn't you see it when you were a bit further away? You can also source examples when we detect a stop sign, but the map thinks that there should be no stop sign, or vice versa. So sort of a map vision disagreement. So we have lots of different ways of sourcing difficult cases, and then we upload images, and we look through them, we label some of them, and incorporate them into a training set. As an example, we've struggled with these heavily occluded stop signs. We found that the detector was not performing very well when they were heavily occluded. And that we have a mechanism in this data engine process where we can actually train these kinds of detectors offline. So we can train a small detector that detects an occluded stop sign by trees. And then what we do with that detector is that we can beam it down to the fleet, and we can ask the fleet, please apply this detector on top of everything else you're doing. And if this detector scores high, then please send us an image. And then the fleet responds with a somewhat noisy set, but they boost the amount of examples we have of stop signs that are occluded. And maybe 10% of them are actual occluded stop signs that we get from that stream. And this requires no firmware upgrade. This is completely dynamic and can just be done by the team extremely quickly. Is the bread and butter of how we actually get any of these tasks to work. It's just accumulating these large data sets in the full tail of that distribution. So we have tens of thousands of occluded stop signs. The fleet can send us as many as it takes. We have the biggest data set for except right turn on stops. I'm basically certain of that. We again create a detector for this, and then we get a noisy stream from the fleet of cars encountering except right turn on stops, and then we can label that, incorporate into a training set. We have tens of thousands of these. I'm not actually 100% sure how you build out a data set like this without the fleet. So I've talked a lot about massaging and growing the training sets, but we place just as much, we put just as much work into massaging the test sets as we do into training sets. So just reporting your mean average precision or reporting the loss function that you achieve in a test set, that just doesn't do it for us. So we spend a lot of time inspired by sort of test-driven development to build out very complicated unit tests and predicates for how the detector should behave in different cases. So for example, we could have a barrage of tests along the lines of, in this image, you should detect a stop sign right here, and the modifier that you, for this and that you predict on the stop sign must be this or that. And so we have mechanisms for creating and massaging these unit tests. It's a growing collection as we encounter problems in the fleet and as we notice them. And then we certify whether this detector is performing well or not. And this is really our test set. It's curated unit tests. If you're in a production setting, we actually break down all these different issues and track them individually and then pursue them one by one with data engine to actually make them work. So occluded signs, we would build out a test set first. We see that we're failing on occluded signs, and then once we have the tests and we're failing them, we then spin the data engine on occluded signs, and then we see that the percent pass goes from 40% to 99% or something like that, and then we're confident that this is actually working relatively well. Now, so I've kind of shown you a little bit of the process we take for even a very simple one prediction, but as I mentioned, there's lots of tasks, lots of attributes, so the complexity of this is quite staggering. We have to know a lot about any scene, and each one of those things has their own data engine. So what we end up doing is we have these neural networks that have a shared backbone, and then they're multitask, juggling lots of different tasks. And in total, the team is currently maintaining 48 networks that make 1,000 distinct predictions. These are just the raw number of output tensors. If you just take all of our networks and you add up the output tensors, it's 1,000. And those tensors, of course, can have multiple predictions in them. None of these predictions can ever regress, and all of them must improve over time. And this takes 70,000 GPU hours to train all of the neural nets. If you have a node with 8 GPUs, you will be training for a year. So we do quite a bit of training there. And all of this is not maintained by hundreds of people. All of this is maintained by a small elite team of Tesla AI people of basically like a few dozen. So how is it even possible to make progress, and how is it even possible that just a small team can maintain so many tasks and get them to work over time? So the North Star for actually achieving this for us is called Operation Vacation, which I'll describe in a second. But basically, the idea is that for any new task, you have a latency to actually the task working. And there's a process, and we understand how the process for getting a task to work. And we're trying to develop as much automation machinery to actually support the development of these new features and new tasks. And we're removing engineers from that loop so they're not involved. We're just building out infrastructure, and then we have a data labeling team and PMs and so on that can actually use that infrastructure to create new detectors. So as an example, we're working with caution lights recently. We're trying to detect when the police car lights are turned on. This is an example of a new task that we'd like to know about. And we sort of have a cookie cutter. We know exactly what to kind of approach to. We know exactly what it takes to get a task to work. All the infrastructure is in place. So this task, we're going to treat it as a landmark task. Landmark is an example of a prototype. So we have a detection prototype, a segmentation prototype, a landmark prototype. And these are just classes of tasks. And if your new task is a member of any of these, or an instance of any of these prototype classes, then all of the infrastructure is just plug and play and goes through the full data engine. You can collect the seed data set, you label your examples, you source more examples in the cases where you're failing, you deploy it to in shadow mode, you source examples, and you grind up metrics, you create all the unit test predicates. All this is completely automated. And this, we're mostly developing the automation infrastructure, and then it's easy to develop any new task, and that's kind of how we get this to work. Okay, so now I'd like to talk a little bit about the neural networks and how they have to change to actually support full self-driving. So what I've explained so far is you take an image from one of the cameras, you run it through this shared backbone, and you make lots of predictions about it in the image pixel space. So we can potentially predict objects, lines, or edges, and so on. Taking the example of edges, where does this go afterwards, right? So here's a video. And I'm showing the predictions of the road edge task on all of the different cameras. And you can see that this is basically a binary segmentation problem for us. And we detect those edges here, and we use this to wind our way through a parking lot because we'd like to go to a certain destination but avoid all the road edges. Now, you can't just drive on the raw predictions of these edges in these two-dimensional pixel pixel coordinate systems. So you have to somehow project this out into a bird's eye view sort of in order to make this make sense. So the raw detections, we project them out into 3D, and we stitch them up into what we call a occupancy tracker. So this occupancy tracker takes all the raw measurements from the 2D images, we project them out into the world, and we stitch them up across cameras, and we stitch them up across time. So the occupancy tracker is keeping the temporal context of that, and it creates a small local map, and then it winds its way through this parking lot to get to the person who is summoning the car at this time. So this is all fine, but there's a lot of problems with actually doing the stitching as I'm describing it. I'm making it sound very easy. The problem is these cameras are pointed in arbitrary directions. They make these measurements in these pixel frames. Your road edges might not even align across camera scenes, and writing the tracker for these edges over time is actually highly non-trivial, lots of hyperparameters, error-prone code, very difficult to develop. So I've shown this example or this visualization a few times in many of my previous talks, where this is sort of the autopilot software stack. On the bottom, you have inputs to the stack, primarily vision. And on the output, we have steering and acceleration. And roughly, you can think of two code bases hidden inside the software stack. We have what I refer to as the software 1.0 code, which is good old-fashioned C++, explicitly designed, engineered by a person. The person writes the code. And then you have what I call software 2.0 code, where the code is an outcome of an optimization. It's the compilation. It's a compiler takes your data set and creates neural network code that runs in the car. And so it's, roughly speaking, neural net. The reason I refer to it as software 2.0 is that you can take functionality from 1.0 code base and put it into 2.0 code base. So this boundary is fluid, and you can actually engulf more and more software 1.0 stack. So over time, since I joined about 2.5 years ago, the neural nets have expanded in how much of software 1.0 land they've taken over. And so the trend is upwards. So in particular, in the case of these road edges, as I've described, what we're now working towards is that we don't actually want to go through this explicit occupancy tracker, software 1.0 code. We'd like to engulf it into neural net code. And we see that typically that works really well. So a lot of our networks have been moving towards these bird's eye view network predictions, where you take all of these cameras and you feed them through backbones, and then you have neural net fusion layer that stitches up the feature maps across the different views, and also does the projection from image space to bird's eye view. And then we have a temporal module, potentially, that actually smooths out these predictions. And this is all neural net components. And then we have a BevNet decoder that actually creates the top-down space. And so then we can directly, potentially, predict these road edges in a top-down view. Now, this makes a huge difference in practice. So here's an example. In top row, I'm showing the left camera, center, right. And I'm showing road edge detections in red. On the bottom row, on the left, you see the ground truth of what this intersection looks like. And you see that the car is positioned on the dot. And so that's the ground truth. On the very right, you see what happens when you take 2D predictions in the images and you cast them out. You basically get garbage. Like, it somewhat works around the car. There, the projection is easy. But far away, especially near the horizon line, a few pixels of error means lots of meters of error. And so these projection-based techniques are extremely hard to get to work. You'd have to know extremely accurate depth per pixel to do that projection. It's a very hard problem. And in the middle, you are seeing some of our predictions from the recent bird's eye view networks that just kind of make these predictions in top-down view directly. So let me show you a video here of what this looks like in practice. On the top, we will have a video of an intersection. On the bottom, I'm showing some of the predictions achieved by the Tesla AI team that has produced these bird's eye view networks. We have road edges in red. We have dividers in green on the very left. Then we have attributes for these dividers. So we want to know if it's an actual curb or if it's just like a logical curb, so like a yellow line or something like that. And then we have a traffic flow direction and a few other things like that. I'm only showing some examples. But the car is on the bottom center of these images. And as we're turning through this intersection, these bird's eye view networks just predict pretty far away the full structure of this intersection and what it looks like. So this is extremely powerful for us. Here's another example in the case of Smart Summon. The car is driving around parking lots, and we have to understand the corridors of this parking lot. And so here we are predicting the corridors in bird's eye view. We're predicting where the corridors meet at intersection points in red, and we're predicting tiny arrows that tell us the traffic flow. And this all comes out of the net directly. There's no occupancy tracker kind of necessary. Here's an example of using this for objects. So on the top, we have our camera feeds. On the middle, I'm showing our per pixel depth predictions achieved via self-supervised learning. We need those depth predictions because we take, as many others do in the literature right now, we take a pseudo-LiDAR approach where you basically predict the depth for every single pixel, and you can cast out your pixels, and you basically simulate LiDAR input that way, but it's purely from vision. And then you can use a lot of techniques that have been developed also for LiDAR processing to actually achieve 3D object detection. So on the bottom, you have then predictions of our detector directly in the bird's eye view. Yeah, here I have one more slide showing just our depth predictions for some other videos. This is not very exotic for any of you who are in computer vision because there are entire workshops on creating videos like these where we are basically achieving depth directly from images. And this is done, of course, no human can annotate depth. So this is done using self-supervised techniques. So in particular, we take an image, we predict a depth. Then when you have a depth for an image, you can cast out all the pixels into 3D, and you can reproject them either into camera views at that same time, but different cameras, or you can reproject them into the future frames of that single camera. And then you have a photometric loss that's enforcing consistency. And so the only way to predict, to make everything consistent in reprojections is to predict the correct depth. And so this learns in a self-supervised fashion to predict depth, and then we can simulate LiDAR inputs directly from vision and use this downstream to make these bird's eye view predictions. And as you might be familiar, the gap is quickly closing in state-of-the-art approaches. If you give yourself LiDAR and how well you can do versus if you do not have LiDAR, but you just use vision techniques and use pseudo-LiDAR approaches, and that gap is quickly shrinking in academia. And we see a lot of this as well internally. Finally, I've shown you sort of how the software 2.0 stack is expanding through the code. It's eating some of the occupancy tracker-like techniques. The logical conclusion of that, of course, is there's still a perception system that creates explicit predictions, and those explicit predictions are, one, shown in the instrument cluster, and two, they are used for a policy. And this policy is still in the land of 1.0, where, for us and for many others as well, where you have explicit planner that takes all the predictions and drives on that. The problem with that is your explicit predictions are basically doomed to never be good enough and never be complete. And so writing these planners is extremely difficult, error-prone, lots of hyperparameters, very tricky. And so the logical conclusion of this, of course, is that we'd like to train neural networks that actually do a lot of this planning inside the network. In particular, we have huge data sets of people driving cars. So when people drive cars and they steer the wheel, they're actually data labeling for you. They're showing you how to drive through any intersection or any other kind of place. And the other thing I'll say is, like, most of what I've described so far relies primarily on supervised learning, with the exception of depth, where we massage and create massive data sets. But we've seen recently with the use of, for example, contrastive losses and things like that, there's a lot of progress today in self-supervised learning, and so we'd like to leverage some of that in a team. Here's an example of just some videos. We have probably the most interesting, largest data set of videos. These are coming from cameras. And so we've been really looking into some of these self-supervised techniques to speed up the process and to speed up the rate at which we learn from very little supervised data. So we don't have to collect like tens, hundreds of thousands of examples of accept, right, turn. We can do it. We prefer not to. OK. So I showed you basically how we are improving the safety and convenience of driving today and how we deploy deep learning into production and support all of the features of the autopilot today. And then I also showed you all of the work we are doing to develop full self-driving, how the neural net is eating through the software stack, and how we are putting vision and AI at the front and center of this effort. So if you'd like to make your AI expertise count, I think there's basically no more impactful or better place to apply some of that expertise than at Tesla today. And if you'd like to be a part of what I've shown you, then come to tesla.com/autopilotai, and you can just directly apply it on the page. It's extremely painless, and that just comes directly to us. And you can help work with us to, and make this all work. So thank you.
Thank you, Andre. That was awesome. So we have time for a couple of questions while Ilya is setting up.
Hi.
Hi.
So when you do these estimations, let's say of a stop sign, and other vehicles in your fleet have driven by it before, do you have a way of incorporating the prior from their estimation, or do you have to re-estimate from scratch?
Yeah, so we do collect maps, we just don't collect high definition maps. Like when a Waymo or something like that is driving through an environment, they know that the leaf on that tree is 15.53 meters away, like to centimeter level accuracy. We don't know about the leaf of that tree, but we do know that there's a stop sign somewhere in the vicinity here. And so we do build low definition maps where we do map stop signs, traffic lights, and things like that, because it provides a second layer. And then also that helps us, again, like I mentioned, it helps us with all the trigger infrastructure for sourcing examples, because we can look for discrepancies between map and vision, and that's a really good signal for us for getting lots of more images of really tricky cases.
So like, I drove by the stop sign yesterday.
Yes.
I estimated it as a stop sign.
Yes.
I drive by it today.
Yes, thank you so much.
Okay, thanks.
Hi, Andre. Thank you for the great talk. I'm very interested in the software 2.0 part, and I follow progress. I think you mentioned it at scale ML. So I wonder, what's your overall vision for this? What are the main findings? Is it something that will supplant programming languages? Will be kind of change the way data science is done? What are your vision for this? And can the community help? Is it something that everybody can use to improve rapidly the whole progress of data science?
Yeah, so thank you. That's a very broad question. I think what I've seen so far is just porting functionality from software 1.0 to 2.0 is not always a good idea. It's a good idea sometimes. You're actually, it's a different way of programming, but you're placing yourself in a very indirect control of the final function. So sometimes you just want to like write a rule. If you're doing it in a software 2.0 stack, everything is so indirect because you're massaging the data set and you're going through a training process that takes days. The iteration is slower. You have to do all of this data engine stuff. So anything that's in the software 2.0 stack like has a cost to it. You're committing to lots of data engine cost, and any new problem that you find suddenly requires a whole data engine pass and curation. And so that's not always a win, it's just sometimes a win. And so what we see actually is we kind of like combine software 1.0 and 2.0. So the older systems, as I would describe them in the software 1.0 stack, they don't always go away. You almost think of it as like sedimentary layers where you have the new functionality, but the software 1.0 is used, for example, to keep sort of guarding rails around the software 2.0 part. So we almost see them as you do a bit of both, and they both have pros and cons. But I do think that the trend, to a large extent, has been towards the software 2.0. It is a more powerful way of addressing a lot of problems that are very messy and really hard to code, and which is a lot of problems in the world. But we definitely see that they come with their own pros and cons.
Thank you, Andrea. We should move on. I really appreciate your time, and thanks again.
Yeah, it's the death wobble.
That is the video of the steering wheel of that truck there shaking violently. Some customers, as you heard him say there, call this the death wobble. Now, despite that nickname it's been given, it's really important to note that we are not, in fact, aware of anyone dying because of this. But in some court papers, a dozen people blame it for accidents.
Action 9 investigator Jason Stujenki is one of the first reporters in the country to tackle this head on and spent almost a year looking into it.
It's a 2011 Ford 250 crew cab, and I'm going down 485. Out of nowhere, it just started violently shaking, out of control. You know the feeling when your stomach drops out.
Jason Kincaid says he pulled over safely, went home, and went online.
And I saw account after account of people labeling it as the death wobble.
I found account after account as well.
Nothing's wrong with the truck.
Frank Plan in Canada sent me this video of his F-250.
Hey.
Justin Hill in Texas sent me his video too.
Yeah, it's the death wobble.
It starts jostling the whole front end, and then where you can barely hold onto the steering wheel. You don't expect to spend, 40 to 50 grand, and and this happens.
I found more videos on YouTube, a Facebook group dedicated to this issue, and this, a lawsuit, a potential class action. It accuses Ford of selling trucks with the so-called death wobble and knowing it. F-250s and F-350s from 2005 to 2019. The lawsuit claims 12 people had accidents and injuries, and that more than 1,200 people filed complaints with the federal safety agency, NHTSA. Complaints like this